Hello guys, welcome back again in this new video. So today we will be covering the next topics and this will be the sequel for the previous video where we discussed about what does space complexity mean. So I have just filled this cell with the red color because these are just the articles on the analysis of algorithms which you can actually see here. See, if you want to actually go step by step what for every video, so you can see this as well. But as of now we are actually not going into these, and we will be just following the excel sheet which we have done, so that's why I have put it red. And so today we will be covering divide and conquer. So here you can see that yeah, divide and conquer introduction. So divide and conquer is only is a like a good technique to follow whenever we have to actually uh, solve the sub problems, and they are always unique sub problems, like they do not repeat their selves in the recurrence relation. So you can see like there in the section there will be four topics. So introduction to DAC algorithm and the DAC technique, recurrence relation for DAC algorithm, and problems using DAC techniques. So first of all, just to begin with the introduction, divide and conquer. In this we have three things: divide, conquer, and combine. So in divide, we divide a problem that's given into smaller sub problems, and conquer means solving the sub problems by recursion until they are solved. And combining combine means combining all the sub problems and getting the final result for that whole main problem. Okay, so some of the standard algorithms that use divide and conquer are these quick sort, merge sort, closest pair points. So basically, like quick sort, in quick sort we have a we pick actually a pivot element and arrange the array elements such that the elements that are smaller than the pivot are in on the left side of the pivot, and the elements that are larger than the pivot are at right side of the pivot in the array. So we actually divide this into various sub problems and recursively sort the sub arrays on the left and right of the pivot element. Okay, and in the merge sort, this is just a normal sorting algorithm which actually divides the array in two halves and then recursively solves them and merges all the uh, sorted arrays, the small sub sorted arrays, into a complete original array that is now sorted. Okay, and the closest pair points is another algorithm that actually can be solved in order of n log n time with divide and conquer. Like we can find the closest pair points in this problem. We have to actually find the closest pair of points that are in a set of like points in the xy plane. So basically there is an xy plane and we want to find the closest pair of points in that plane. So we can actually go through all the points and actually calculate the distances and compare for every distance to find the minimum. But if we use divide and conquer, then it can be solved in order of n log n time. Okay, now Stresson's algorithm is also can also be done with this. Like in this actually it is used to like when actually we multiply two matrices, it generally takes order of n cube time. But Stresson's algorithm has some formulas by following which we can actually do it in less than order of n cube, that is order of n to the power of 2.8974, which you can see here. Also for fast Fourier transformation algorithm, which is this Cooley Turkey fast Tukey, not Turkey, sorry, Tukey fast Fourier transformation algorithm is the most common algorithm for fast Fourier transformation. It is using this divide and conquer to solve it in n log n time. Okay, and Karat-Suba algorithm for fast multiplication also is there, which actually does the multiplication of two n digit numbers in at most 3 to 3n to the power log 3, 3 to the base 2, that is about 3 into n to the power 1.585 order. So these are actually some of the algorithms that actually can be solved using divide and conquer. But the thing is that these that the algorithms that use divide and conquer have to solve the sub problems given there, uh, like sub problems, and not that we discard some of the sub problems and then like you can see in the example that in a binary search. See here in the binary search where we have to actually search for an element. So what in this what we do is we take a middle element, and if the target value which we have to find in the array element is less than the middle, then we search in the left side. Otherwise if it is greater than the middle, then we search in the right side. So uh, and like this goes up to dividing those in n sub problems, and it takes order of log n time. Okay, because there will be like order of log n steps for the division of every sub problem. So there will be order of log n levels. So that's why it will be taking order of log n. But this does not qualify as a divide and conquer, because it is more of a decrease and conquer type of algorithm, because we are decreasing the size of the array. But in the real divide and conquer, we do not decrease the size of the array, but we search in the smaller sub array. Okay, uh, and you can see this divide and conquer algorithm. It can be shown here as there is an array, we have indices I and j. So if we see that is like the main thing is here is that you do not I do not see this as a whole, because you will get confused. So just see that we first divide this into smaller sub problems, as we showed here. See here, divide, conquer and combine. So the first step is divide. Okay, so first we will divide, then conquer, where we have to divide that like solve those sub problems, and then combine the uh, sub problems. Okay, and return the uh, final answer D. Alright, so now recurrence relation can be shown here. Like see, as you know that this is a new function that will divide this array into sub arrays. So you can write it as function 1 of n, and these will actually solve these problems. So it will almost take time as n by 2, and here as well, because we have as we have divided that main array into two sub halves. So that's why n by 2 is here. And at last we will combine. So this combine algorithm will be just we can write it as fn sorry f2n. And that's why the recurrence relation can be written as, when we add these all, so it can be written as fn plus 2 times t n by 2 plus f2n. And it will take order of 1 if n is small. Okay, so this was the recurrence relation. You can see the example here as well. See the minimum and maximum. So actually what we have to do in this array is we have to find the minimum element in the array and the maximum element in the given array. So minimum you can see it's 70 and maximum is 250. So basically I'll just explain you this problem. Wait, you I'll just go to the code and explain you what it's actually doing in the code. So see, this is a C++ implementation, but the algorithm remains the same. So let's say you first I'll show the minimum part. So let's say you are given an array that is 120, 34, 54, 32, 58, 11 and 90. So here you, if you need to find the minimum element, as we can see here it's 11. So just remember this, and let's see the algorithm here. So here DSC min is the algorithm which will take array as the input, index that the starting index, because we will be only starting with the first element to actually find the minimum, to compare them for the minimum, and uh, this L, the length of the array. Okay, so in this you can see that first we will actually go step by step up to the last element. Okay, last these two numbers. Okay, so first we will run like we will call the recursive function up to when we get up to the second last element, because we have to compare this and the last element as well, and then we will backtrack with from the stack, as these will be stored, the levels will be stored in the stack because we are using the recursive function. So we will backtrack. First we will see, we will compare these two. Is 11 less than 90? Yes it is, then we will return 11, then minimum will be 11 here. See, minimum will be 11 here, because array index then we will like minimum will be 11, and we will compare with the previous index element, because in the stack the index element here, uh, here which was passed for that last call of stack, uh, will be 58 here. So we will compare 11 with 58, then we will check if array of like is 58 less than 11. It is not, then we will return 11 as well here. So same, 11 will be returned, then we will check with 32, as it is less, then we will check with 54, with 34 and 120. At last we will be returning minimum, because all 11 is less than all the elements, so we will get minimum as 11. And same is the case with the maximum, just we have to actually this change this less than to greater than symbol only in these two parts, and all and other all things are same here. Okay, so when do we use need to use actually divide and concurrent dynamic programming? See, in dynamic programming we also actually solve the sub problems, but the sub problems solved there are actually repeated multiple times. See, but in divide and conquer the sub problems are not repeated, as I told you in the beginning. So you can see that in here, see, for example, quicksort is a divide and conquer algorithm because we never evaluate the same subproblems again. But on the other hand, for calculating the nth Fibonacci number, dynamic programming should be preferred, where we actually in dynamic programming memoization is there, so that we will cover later on. So that's why we have to actually see to the problem as what is happening, and apply these divide and conquer or the dynamic programming accordingly. So yeah, this was it for today, and we will be covering the binary search in the next video as well. However, I have just told you about the binary search here in brief. See, here I told you that why is it not divide and conquer and but decrease and conquer algorithm. So yeah, stay tuned and keep watching and keep learning. So thank you guys.